see a chart that's just packed with numbers and feel your brain kind of short circuit? Yeah, you are definitely not alone. But what if I told you there's a key that unlocks this whole world of statistics, and it's way, way simpler than you think? Let's go find that key together.
So be honest. Does this question hit home? If you're nodding right now, I totally get it. It's that little bit of a cold sweat you get when someone brings up a p-value in a meeting. This statistics anxiety, it's a real thing. But trust me, it's not a life sentence.
And we're going to fix this, not by trying to memorize 100 different formulas, but by zeroing in on this single biggest, most common mistake people make. Once you really get a handle on this one thing, it just unlocks a whole new way of looking at data.
So here they are, the 9 most common statistical traps. Kind of looks like a minefield, right? But I want you to look closely at that very first one, presenting and analyzing data types incorrectly. That's our starting line. And here's why. If you get this wrong, you're pretty much guaranteed to fall into all the other traps, like, mixing up correlation and causation. Master this one idea, and the rest starts to fall into place.
So, what is this big number one mistake? Well, it's actually shockingly simple. Not truly knowing your data. This is the absolute bedrock of any good analysis. I mean, before you can do anything cool with data, make a chart, find a trend, anything, you have to understand what you're actually looking at.
So at the highest level, all data basically splits into 2 big families. On one side, you've got quantitative data. Just think quantity. This is stuff with a real numeric meaning, things you can actually measure or count. And on the other side, we've got categorical data. Think category. These are just labels or names or groups that describe some kind of quality. And we can even break it down a little more. Quantitative data can be discrete, so whole, countable things like the number of kids in a family. Or it can be continuous, things you measure like height or weight that can take on any value in a range. And then categorical data has 2 flavors too. There's nominal, where the categories have no real order, like cat, dog, fish. And there's ordinal, where there is a clear order, like say high school, bachelor's, master's. Okay, now this slide shows a classic trap. Take a look at those location or education columns. You see numbers, right? 1, 2, 3, 4, and your first instinct might be to, calculate the average. But that would be completely meaningless. These are just codes. 1 might mean urban, 2 might mean suburban. The big takeaway here is, just because you see a number, it does not mean you can treat it like one. You have to know its true identity, or your whole analysis is broken from the start.
All right, so we've learned how to identify our data types correctly. That's step 1, and it's a huge step. But, data rarely lives in a bubble. The real magic happens when you start to understand how different pieces of data influence each other. And this leads us to the next big question. Does being in one group change the odds of being in another?
And the tool we use to answer that question is called conditional probability. Now, I know it sounds a little fancy, but the idea behind it is incredibly simple. It's just the chance of something happening, given that something else has already happened. It's really just an if this, then that for probabilities. We write it as PA/B, which you can just read out loud as the probability of A happening, assuming B has already happened.
The absolute best way to make this idea really click is to see it in action. So let's use a little story. Imagine a tennis match. The outcome of that second set probably depends a lot on who won the first set, right? That shift in momentum and confidence. Well, that's conditional probability playing out right in front of us. This thing right here is called a tree diagram, and it's a fantastic way to map out all the possibilities. See how that first split shows who could win the first set? And then each of those branches splits again for the second set. And here's the really cool part. Notice that the chances on those second branches are different. They totally depend on what happened in that first set. So let's put some actual numbers on this. Anne has a 70% chance of winning that first set. Now, if she wins it, her confidence is sky high, and her chance of winning the second set soars to 80%. But look at that last line. If Colin wins the first set, Anne's chance of winning the second set plummets down to just 40%. The first event completely changes the game for the second one. Okay, so here's the payoff question. Using our little map here, how can we figure out the chance that this whole match is over and done with in just 2 sets? That means one player has to win both sets back to back. How do we do that? Well, we just have to follow the branches. To find the probability that Anne wins the first set and the second, we just multiply along her winning path. So 0.7 times 0.8 gives us 0.56. Then we do the same for Colin. 0.3 times 0.6 is 0.18. Now, since the match is over if Anne wins twice, or if Colin wins twice, we just add those two possibilities together.
And there it is. There's a 74% chance this match is going to be decided in just 2 sets. See that? We didn't need some scary formula. We just used logic and this idea of conditional probability to figure out a real problem. Now that we actually get the idea, let's look at the formal math behind it. Don't let the symbols intimidate you. All this is saying is that the chance of A happening, given that B already happened, is just the probability of both A and B happening divided by the total chance of B happening in the first place. It's really just a formal way of writing down the exact same logic we used on that tree diagram. An event diagram like this shows it perfectly. Think of that whole circle B as our new universe, right? We know for a fact that event B happened, so we're only looking inside that circle now. The probability of A times also happening is now just that little overlapping part as a piece of that entire B circle. Okay, let's bring this all home. We started by tackling the #1 mistake in statistics, just knowing your data. And from that one simple idea, we've unlocked a much, much smarter way to think about how things are related in the real world. So if you only take away 2 things today, let it be these. First, always ask, am I looking at a real number I can measure, or is this just a label for a group? And second, always ask, are these 2 things related? Does one thing happening actually change the odds of another thing happening? Hey, remember this list of mistakes? Well, by understanding conditional probability, you are now so much better equipped to deal with tricky things like number 6, correlation versus causation. You can now ask a much smarter question. Okay, is it just that 2 things happen together, or does one thing happening actually change the probability of the other? That is a game-changing question, and now you've got the tools to start answering it. So the next time you see a statistic in a news headline, just pause for a second. Ask yourself, what kind of data is this really? And what's the relationship that's being claimed here? You might just be surprised at the new level of insight you find. And that is how you go from feeling anxious about statistics to feeling empowered by them.